Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. Thanks for making time during one of the busiest days in a year. Today, we have two speakers from the University of Maryland. Cody Dunn is a PhD student in computer science department at the University of Maryland, working with Ben Schneiderman. And Elizabeth Bonsignor is a PhD student in iSchool there, and she served as an operations engineer and intelligence analyst for the Department of Defense. And she holds master's degrees in computer science and education. Actually, they are on their way to the I3 conference on social computing in Vancouver, Canada. So today, first they will talk about the paper they will be presenting at the conference on Sunday morning, and then later they will talk more about the network visualization Nirvana and readability metrics for the graph drawing. Okay, here comes the talk.
Thank you. Thank you very much, Bongshin. As she said, I'm Elizabeth Bonsignor, and with Cody's help today, I'd like to share with you the results of a study that we had this past spring, studying the teachability of social network analysis using NodeXL. As you can see, we both worked on the project, but also Dana Rotman, another PhD student at the iSchool, was with us. Mark Smith, a sociologist with Telligent. Tony Capone, who's actually here with us today. Thanks, Tony. He's a developer. And our professors, Derek Hansen and Ben Schneiderman. First, a real quick overview of what I'm going to cover today, or what we're both going to cover today. First, the motivation and research goals for the study, which focused on an evaluation of NodeXL to teach as a teaching tool for social network analysis. And the principles of layout or graph principles that we dubbed NetViz Nirvana and readability metrics. The research methods that we went over, some samples of student work, and some lessons learned. The motivation for our study is based on the observation that sophisticated network analysis tools are basically remain the domain of computer scientists who are developing algorithms for drawing graphs. Most of them have high learning curves, steep learning curves, use command line interfaces, or require some level of programming expertise. Yet, as most of us know, social network analysis is important in academic, commercial, and in social media contexts. In short, SNA is not just for scientists anymore, because community managers also have a stake in learning how to use SNA tools to sort of help their communities to cultivate. So our long-term goal is to develop accessible tools and educational strategies to help reach a broader spectrum of users. With that overarching goal in mind, the focus for our talk today is the evaluation of NodeXL as a teaching tool for social network analysis across a broader user set, as well as these graph layout principles that we've dubbed NetViz Nirvana, which Cody will go over. First, a little bit about NodeXL. NodeXL is an open source plugin from Microsoft Excel, and it stands for Network Overview, Discovery, and Exploration for Excel. As an open source plugin for Excel, it takes advantage of the spreadsheet format to store your network data. It also takes advantage of the standard spreadsheet manipulation tools such as sorting, filtering, and creating formulas to actually use them in your displays. If we take a little walk around the layout, basically we have on our left, we have the spreadsheet, your data for your nodes and your edges, and we have the visualization. We have worksheet tabs that you can switch back and forth between tasks for edges and nodes and clusters. And it's a very tightly integrated visualization and data. If you click a node or an edge in your graph, it will be reflected or highlighted in your cell data in your spreadsheet, and vice versa. You can import your network data from existing spreadsheets, of course, or from several common social network data sources such as Twitter, or even from tools such as PIAC or output from PIAC. They also provide a starter library of basic network metrics, such as centrality measures and degree measures, which you can select as needed based on your performance requirements or based on what questions you're asking. You can also have multiple ways to map your data to display properties or attributes, such as using degree to represent size, shape, or opacity of the nodes, or you could even use thickness of the edges as well. And on to NetViz principles.
So as part of our study, we introduced these information science students who had this couple of week class on network analysis to these principles for creating better network diagrams that we call NetViz Nirvana. And NetViz Nirvana pretty much says that every node in your network should be visible, so you can count the number of nodes in any particular area, and so if the nodes are large enough, you can read the labels on them without them including each other. Also, we want the degree of every node to be countable, because degree ends up being a very good measurement for how important any individual node is for the status of any actor in the network. Also, we want to be able to follow each of these edges from the source node to the destination node, because knowing that relationships exist isn't nearly as useful as being able to find out who they're between and look at more details about them. Also, we want to be able to easily identify clusters and outliers, because that's what we really care about finding. If we're a network analyst, we want to look at these interesting attributes of our network. So these overall principles was the introduction that we gave them to creating good network diagrams, but they don't really give you fine detail as to where your drawing is, where problems are in your drawing, and provide a quantitative measurement for how good or bad your drawings are. So we've been working on these readability metrics, which we also introduced to the students during the course, that are just measurements for how readable or understandable the drawing is. And so some of these are common things like edge crossings that we've seen before. And we also have a node occlusion metric for nodes overlapping, and you have edge tunnels for when edges travel underneath them. But we're defining all of these on a continuous scale from 0 to 1, where 0 is the worst possible case we think you could have, and 1 is the best case. In the past, these have often been called aesthetic metrics, but we believe this is a little bit of a misnomer because we're focusing on the readability of the drawing, not necessarily the beauty, although it's fortunate that beauty is oftentimes correlated with readability. Now, in the past, people like Purchase have focused on global metrics, which give you a single number for various aspects of your entire visualization, saying it's 80%. On node occlusion, or 80% on edge crossings, things like that. But oftentimes this isn't sufficient to guide users to the problem areas so that they can improve their drawings. Think of an analogy to Microsoft Word. If Word just told you that you had 20 misspellings in your document rather than pointing you to where those misspellings were, it would take you substantially more time to improve your document and get it ready for publication. So we've created these node and edge readability metrics that give us this fine granularity and allow us to pinpoint the problems. First off, let's look at node occlusion. In this simple drawing on the right, we have nodes A, C, and D, and this fourth node that we can't see because A is occluding it. And there could also be additional nodes hiding under there that we're not able to count because they're completely hidden. But by moving A off to the side, we can read the label on node B. We see that A is not actually connected to node B, and it's just a much better representation of the drawing. Our occlusion readability metric is proportional to the area lost if you compress all of the nodes into a single static image, like layers in Photoshop or any other image processing application. So when you flatten all of these nodes, you count how much area is lost in the flattening. And in a perfect situation, every node is uniquely distinguishable. They have a white border around them or whatever their background color is, and you don't lose any of the area. And in the worst case scenario, they all end up in a little pile together. Our edge crossing readability metric is the same as that used by Purchase, which is the number of crossings that you count in the drawing, like this intersection here, scaled by an approximate upper bound for how many we think there could be. And this is bad because when you have crossings like this, it's extra visual complexity in the graph. If you don't need to have the crossings there, you should eliminate them so that users can do things like pathfinding tasks better without having to deal with these visual attributes. Right? And so by moving it down, again, we get the same representation where you don't have these intersections and this extra cognitive load. The edge tunnels are when you have an edge traveling underneath a node without actually connecting to it. So this is the exact same network as before, but because of the positioning, it looks that C is not directly connected to B, and it looks like A is connected to B. But in fact, the edge was just hidden directly underneath that node. And so this is kind of a trivial example where things are perfectly aligned, but oftentimes it's very hard to determine whether an edge is actually connected to a node, especially if you have non-circular nodes. So just like edge crossings, we create a metric for this based on the number of tunnels, based on an approximate upper bound for how many there could be. But we define these additional local edge tunnel and trigger edge tunnel metrics for how many edge tunnels there are underneath any particular node, and how many edge tunnels there are caused by the edges coming from a particular node. And so the first is good for identifying nodes that are problems, and the second is good for identifying areas around nodes that we might want to manipulate as a whole. We also look at text readability, and so the first we examined was that label height, or the height of the text within the label, and guidelines for proper text height, and of course depends on the font and all that, but usually it should be within 20 and 22 minutes of arc from the viewer's eye. And so no matter what the medium is, we have to calculate the distance of the user from the medium, the pixels per inch in the medium, or the height of the font in inches on paper, and compute this visual angle. And we create this metric based on approximate lower and upper bounds based on work other people have done. Finally, label distinctiveness is a measurement for how unique your label is in the drawing. If you have Department of Computer Science, a Department of Sociology, and so on as your node labels, and then you truncate after 8 characters, you're going to have all of these labels that you're not going to be able to distinguish between them. And so we create this distinctiveness metric based on a prefix tree where you can just cut off at your truncation point for all of your labels, and then in each of those subtrees you can count the number of nodes that have identical labels. Now, one thing that you might think is, why don't you just use like Likert distance or things like that to determine the distance between every node, or between the label of every node? But this would, in fact, encourage users to create arbitrarily complex and unnecessary convoluted node names rather than just differing by a couple of characters.
Thanks, Cody.
I'm sorry.
We tried to frame our methods onto our methods. We tried to frame our methods along 2 axes, if you'd like to think about it that way. One is depth and one is diversity. We say depth because we wanted to use mixed methods and a long time frame to study these users, because we wanted to learn the graduate student, the information science graduate student's process of learning social network analysis, their sort of sense-making process. We also wanted to try to map out or document the discovery process that practitioners, experts, might use as they are trying to find patterns in the social structures. What we found was that there's a qualitative framework known as multidimensional, in-depth, long-term case studies approach. It's a qualitative approach, and it assumes at the outset that exploration of data sets, complex data sets, cannot be effectively tested by predetermined, timed traditional timed usability tests that usually last around on the order of 1 to 3 hours, because that sense-making process is really not that predictable. So we felt that that was ideal for studying basically the learners as well as the experts. We took a tube to sort of meet our diversity need, which is to support a broad base of users. We had a 2-pronged user study. We used a core set of methods, interview techniques, and pre-survey and post-survey, but we placed them, or we used them against 2 different groups: the computer scientists who had background in graph drawing and information visualization, and information science students who were interested in social networks and online communities, and were in fact studying online communities, but weren't necessarily as technical as a computer scientist and didn't really know that much about graph drawing. So first, for a little bit of background on our information science graduate students, we had 15 of them. They're a mixture of information science or library science and information management. They were all participating in a communities of practice course to study online communities and to determine social structures and relationships and ways in which they could help cultivate these online communities. They were each studying a community of choice. They ranged from things like a depression support group, a Serious Eats gourmet group, a weight loss group, wedding planning group, an arts and crafts group, a records management listserv, and so on. The time frame for our study was about 5 weeks within a 16-week semester. The data that we collected is we observed in class, in lab. We transcribed some of their online discussions and sort of coded and categorized what they were talking about as they were learning social network analysis. We had individual observations of various students, of just about all of them, 13 of them, while they were completing certain assignments using NodeXL, and sort of what they would use a talk aloud protocol. So they would say, I'm thinking about this, or I'm really frustrated about that. We looked at their coursework, their assignments, and they had diaries. They had journal entries that talked about, this is where I'm at in my visualization process, this is what I'm thinking about, these are my hypotheses. We did a pre-survey to determine what their level of experience was, and a post-survey to sort of determine what they thought was most important. And for a few selected students, we did some in-depth interviews. We used a grounded theory approach for an analysis, which basically says that you have, after you have all this data transcribed, you sort of code and categorize all the salient features. For the for the computer science graduate students, that was primarily conducted by Cody. He had 6 computer science graduate students. They were all experienced at some level in graph theory, social network analysis, and information visualization techniques. So he took sort of a core of what we use for the information science students. He used a survey, a pre-survey, and then took about just under 2 hours with each participant to give them a tutorial and to observe them interact again with their own data set, not with a prescribed data set, but with a community or a social network that they were interested in. And part of that observation process was an in-depth interview. Again, a grounded theory approach, and Cody also used Spotfire and some quantitative analysis of the surveys. As we were coding and categorizing some of the transcripts, and especially the online discussions and the journal entries, some salient features about teaching social network analysis and the learning process came to mind, which was basically the students really enjoyed being able to map their display attributes of using certain metrics to their display. In other words, they wanted to make the node sizes big if the degree was high. They wanted to change the shape of certain nodes that had certain characteristics, like were community moderators. And we found that NodeXL very effectively supports this, being able to do it very dynamically and setting it pretty much via a menu item. And the students became almost obsessive after they learned about the graph layout principles known as NetViz Nirvana. Although they didn't have the capability built into NodeXL yet, they found that really important to do to try to make these meaningful graphs, and that actually helped them develop relatively sophisticated graphs in a short period. Some student examples. I'm going to go through 3 of them, and the first 2 sort of have the same structure in that, or goal, in that they were interested in finding whether boundary spanners or bridges occurred across different subgroups or across different forums. And they both used degree and tie strength to sort of represent that as their metrics to represent that. This student, she had this Subaru subgroup, Subaru car owner subgroup in the carspace.com community. Again, she identified boundary spanners, and she wanted to show the levels of participation in different forums. So these spheres here are the actual forums that she was interested in, and the smaller nodes and triangles and diamonds are the actual people that are part of that community. What you can see right away is that the Meet the Members and Cafe forums have a lot more connectivity, a lot more common participants. This is probably because of their more relaxed nature, or the broader nature of their discussions, than the problems and solutions group. For the problems and solutions group, many people just go in and ask a question, and they're out of there, and they don't keep coming back and making friends. Another thing that we found that was interesting, or that she found that was interesting, was that the hosts, which ostensibly are the people that are supposed to keep the discussion going, were in fact some of the lower level participants in the group, with the exception of this one right here. But in fact, who came out as community leaders were these 2 little triangles, and they didn't necessarily have any real leadership role, but they came out just based on their participation. The second group is this student. Again, she wanted to identify boundary spanners across these different subgroups, but she also wanted to try to find out how these ravelers, who are people who knit and crochet, actually what the properties of those folks who completed more projects, more knitting projects or crocheting projects was. What were the sort of factors that led them to complete more projects? And so she picked the top 20 posters and contributors of 3 different groups. One was Lazy and Godless, and which is the LSG community. The other was Fiber Arts and Project Spectrum. And what you find right there is they're pretty much tightly unique and separate subgroups. In this first drawing here, there's not very many boundary spanners across the groups. They sort of stay among themselves. And you also see that the lazy and godless community, they're very much more social because they contribute a lot more to the posts, whereas Project Spectrum is really kind of focused on completing projects and just maybe highlighting that fact in their posts. In the next post, she took only in the next visualization, she took only the bloggers with that community, and the community moderators or leaders of each subgroup are shown by the spheres, and it sort of confirmed the relatively simple hypothesis that that those who were moderators or those who participated more actually completed more projects. But it's still an interesting visualization. And while this student didn't really achieve NetViz Nirvana per se, because there's lots of edge crossings, he's really interesting in that he tried to model a sort of a community management problem using NodeXL, and it was really pretty effective at doing that. What he has is he has a records management listserv, and he was trying to identify what features of the different people would be reflected in their sort of leadership and experience levels. And his hypothesis was that those with high betweenness centrality and those who are connected to important people, those with high eigenvector centrality, would in fact turn out to be the leaders in the community. And that held true because the admin in this left graph, you see that the admin of the listserv community was in fact, he had the highest betweenness and eigenvector centrality. Those with lower betweenness, or those who are less connected, I guess, to or bridging across different subgroups, are sort of hanging out on the periphery, and they're in the red as well. What he tried to model, once he confirmed that was sort of his that his hypothesis was correct, was who would be the best candidate if he could skip or take out that existing admin, or if that admin left the community. Would there be anybody who could sort of have the same requisite skills and experience and connections that would be able to come and fill that person's place? And he did, in fact, he skipped the node using NodeXL, very easy one step, and was able to show that there was a new admin that sort of popped up there. So relatively sophisticated model for somebody who'd only learned for about 3 to 5 weeks. So as to our lessons learned, what we found primarily was that when you promote the awareness of NetViz Nirvana, people learn it. When they know that you have to make graph layouts that are readable, they learn it pretty well, and in fact they get sort of obsessive about it. One thing that NodeXL didn't support very well, that the students had workarounds themselves, is they tried to scaffold their learning with a sort of interaction history. They would save different versions and different paths that they followed with their visualizations and their hypotheses as they went along, but what they really kept saying was, if we could have a history or a way to undo actions, that would be really helpful for us to learn. You know, I thought of this idea, it didn't quite work, and it might also be good to have a library of those sorts of histories so that other people who learn, or who are learning social network analysis, could sort of learn from that as well. There were some pacing issues. They went from a nice tutorial with some, low levels, numbers of nodes, and then went very quickly to lots of nodes, and it got a little bit hard for them to take it all in. And many of them said that they would have liked a higher level of Excel experience, if not just Excel itself, more experience with the interface of Excel 2007. For researchers, what we found is that MILCs are a very effective way to sort of represent the discovery process that subject matter experts follow as they go through their analysis of these complex data sets. And it maps the sense-making process that students follow as well. And in fact, if you consider that of the 132 reports or articles that were posted, I guess, between 2005 and 2008, and 2007 and 2008 in InfoViz and VAST, only 39 of those actually had any user evaluation period, and all of those were between 1 and 3 hours. They were all your standard timed, predetermined data set analyses. So this was probably a good example of trying to map to the actual process of learning SNA as well as the discovery process. Of course, it's kind of obvious, but it merits mention that does require more data collection and analysis.
So from our CS students in particular, but also our information sciences students, we learned a lot of more specific things about our tool and about tools in general for how to improve them. So we've shown again that multiple coordinated views, like having our tabular view and having the visualization and the brushing and linking between them, is very effective in allowing people to analyze the data. And we've also shown that users enjoy being able to code all these visual attributes based on the data that they have. More interestingly, we showed that adding readability metric interactions is helpful in getting these users, adding knowledge of the readability metrics anyway, is more helpful in getting these users to better finished productions than without them. Also, more specific to Excel, we found that having that tabular view with all these formulas and macros that you can apply in Excel allows for very extensive and novel data manipulation techniques, like writing formulas based on constants they define elsewhere and then manually tweaking them and seeing the reflected visual updates. However, being inside Excel, we're limited to what Excel templates allow us to do. So, like Elizabeth said, having an undo functionality or having a little hierarchy of previous actions and being able to go back to them would be very helpful for these tools. And finally, the big key point is that users would really enjoy being able to aggregate nodes and edges. And currently, NodeXL has a limited edge aggregation functionality, but users constantly requested better aggregation techniques, and not just for communities, but for user-defined groupings as well. Like if you're looking at an email network, you might want to combine email addresses that you know of that belong to a single particular person. In conclusion, we used two different and diverse groups, one with a nice long-term, multidimensional, in-depth long-term case study, and another with more short-term, focused, intense assignments using their own data sets, and they were all invested in accomplishing their analysis. For network analysis education, our information science students showed that NodeXL can be very useful because of its shallow learning curve for teaching basic network analysis techniques. And as far as NodeXL usability and design, our feedback from our CS users and our IS users gave us lots of information about feature requests and bugs for NodeXL that allowed substantial improvement even over the course of the user study in the program, and we're just finishing a large redesign of the user interface based on some of these requests. Okay. If you have any questions, you can ask them to us now, or you can look at a tutorial for NodeXL, 50 pages here on the Kasky website. Here's the NodeXL website. And then here's more visualization links at University of Maryland.
Thank you.
Cody, what are you doing to actually compute these readability metrics today? Are you doing computational analysis of the geometry of the graph?
Yeah, so we just look at the layout provided to us by the layout algorithm. And then we're able to find the number of edge intersections, and we're able to find where every node is occluding. And the current implementation we have, which I'll talk about a little bit more in Social Action, which is another network analysis tool, uses fairly naive approaches for computing these intersections. But if you look at the work by, he's at University of Maryland. You know, I'll send you the link. But there's a large reference library of fast edge intersection and line intersection and rectangle intersection algorithms that you can use to substantially improve this process. Because in the best case scenario, you'd be computing these in real time and giving feedback to the user as to where the problems are in the network.
Yeah, I had a question about that. So the current tool doesn't give them feedback on the sort of readability metrics?
So NodeXL currently doesn't, although it will soon. But actually, I have a follow-up little addendum presentation that talks more in depth about the readability metrics, and I think your questions will be answered there.
I'm sorry I missed the beginning, but is it sort of a manual layout tool that doesn't do the kind of, edge crossing removal that they somehow have to sort of...
So NodeXL has a couple of layout algorithms that it provides. We have the Fruchtman-Reingold algorithm, an older force-directed approach. We have Harrell and Korn's multi-scale approach now for laying out the graph. Circle layouts, various, like sine waves and grids and spirals and things like that.
But can the user then somehow make it better if the algorithm doesn't do satisfactory?
That's what all of our iSchool students did.
And in fact, they spent lots of time. Although they didn't have it done for them, or at least not yet in NodeXL automatically, to sort of remove all these edge crossings. They spent a lot of time in all their diaries and all the interviews that we had with them. Once they were aware of NetViz Nirvana, once they had read Cody's paper and Ben's paper and learned about all these different factors, node occlusion, edge crossings, and edge tunnels, they really spent a lot of time saying, I want to get rid of them and make my drawing more meaningful. So in a relatively short time, they were able to get a really sophisticated sort of idea of how they should be drawing graphs manually. It's really important to
They
them.
did that via dragging.
Yes, and they learned how to, they liked locking certain, they really liked locking certain sections of the graph and then experimenting with other ones as well. So yeah, I mean, it was really, I mean, they got obsessive about it actually.
Yeah, so you said that when they learned, they were obsessed about it. So when did you teach them?
It was right, it was the, let's see, they had a tutorial in NodeXL, they read Cody and Ben's tech report and then they discussed it in class. And they were, and around that same time, they were just now starting to sort of import the data for their communities and saying, this is what I kind of think will happen. And they started realizing, oh, this looks really crappy, or, you know, or they didn't like the way that it looked when they did the first automatic layout, and then they would play around with it.
So what was the exact task you guys gave to them? Like, what did you ask them to do?
They had these online communities of interest that they had started to study, and they were using various communities of practice ideas to sort of determine better than participation metrics what they were, more information about how to sort of keep these communities growing so that they wouldn't die off, as we see many online social networks die. And so this section for NodeXL was they wanted to see how social network analysis tools, statistics, and visualizations would help them, give community managers more of an idea of these sorts of things. So they learned NodeXL. They were given 2 assignments to say, sort of state a hypothesis about something that either a management problem like that third student did, or ways of sort of highlighting the interests of subgroups, and then make 2 visualizations based on that, sort of initial visualization to see if it confirms your hypothesis or shows you something else, and then a second visualization that either models some sort of problem or looks at it from another facet. Does that answer your question?
Okay. And what was the average size of the graphs they handled?
Oh, that's a good question. It was anywhere from, well, with the lost PD, there was one student studying lost PD, and I am actually not sure. I think she might have actually looked at 2 different subgroups, and I don't remember. I think that was probably the top end, but they were on the order of, the hundreds. So
some of our CS users dealt with much larger data sets. We had one analyze a protein-protein interaction network of 10,000 nodes and 40,000 edges, and we had another look at the vast 2009 challenge data set of flitter relationships, which is a Twitter clone that they made up for the data set. And in the current version of NodeXL we were using at the time didn't handle these very large data sets very well. And so we got a lot of good feedback about how to reduce the burden placed on the user of sitting there and waiting for things to finish. So we received feedback on disabling some of the real-time updating and more progress bars and being able to cancel actions and the like. And so currently NodeXL is more your introduction to social network analysis tool, but as we progress it scales more and more to larger networks, and we actually have a research assistant working now on porting some of these algorithms like betweenness, centrality, and the like over to NVIDIA's CUDA architecture for graphics processors to improve the speed of them. And then we have Vladimir Barash working on porting them to a MapReduce framework, so you can offload it into the cloud for large networks.
So for the first user group, you guys gave us like 3 examples. Do you have any examples for the graduate students?
Not in the slideshow, but I can bring them up if you like. They didn't learn NetViz.
Maybe I can see it.
Yeah. Sure. Yeah, and so they were different tasks. It wasn't about the communities of practice approach. Well, I gave them more directed tasks like find an interesting community and find an interesting actor and then highlight them in the end visualization. But they didn't have nearly as much time to go through and explore it fully and arrange the final layout for a publication.
Yeah, I have one more question. Actually, those NetViz Nirvana thing, to me, nothing is quite surprising. So even though you don't teach the user may still try to achieve that kind of thing. For example, if someone gives me a graph, the first thing I would do is remove edge crossings and then make them, like position them at the right location so that it distributes over the screen and so on. So how much do you think it affected them, like the fact that you taught them before they started?
And that's a great question, because at around the same time, a little bit after Derek Hansen had started this community of practice course, a colleague in the business school, in the B school there, had a sort of a 2 assignment. I think he had a 2 course, so it was over 2 weeks assignment for his business students who were pretty well versed in social network analysis, the metrics, the statistics end of social network analysis, but they didn't really care so much about the graph and the information visualization part. They were not told anything about NetViz Nirvana, and in both their assignments and in their write-ups and in some of the surveys that we had of them, their graphs, they didn't try to do anything other than the standard layout in NodeXL. And they said, yeah, we think the statistics are more important because I can look at a number and it means more to me than looking at the structure, because this is kind of a hairball right now, and I don't really care about spending time working on it. Part of that might have been that they only had 2 weeks instead of the 4 to 5 weeks that the other students had. But we also, like to think that part of it is because they didn't really care about whether it looked pretty or not, or whether it looked meaningful or not.
We're also trying to be able to teach social network analysis to students who have no graph theory background whatsoever. So they don't know what a node or an edge is when they start. So giving them this leg up on creating these better visualizations saves them some time later on.
And most of the IS students, the library science students, really didn't know what a node or an edge was when they started.
I have a related question. So you said people get obsessed trying to...
At least the 15 that we worked with.
Right.
Yeah.
So how, do you have an idea of how long they spent?
Yes, we did. I mean, it was somewhere on the
That'll be an
average of,
interesting
it was somewhere on the average of per assignment 2 to 3 hours that they would sit and play with the
And this is for
diagrams
single
and
graph,
test
or
things.
this is for exploration in steps where they...
This was probably for exploration in steps to complete their final visualization that they submitted for assignment.
And
Now, overall, for all the assignments, I had some numbers, but they spent about 10 to 12 hours, he said, an average of, I guess the fastest person spent about 3 hours for his visualization, and at the high end, or the median, was probably more like 8 to 10 hours.
So that is a big chunk of time. Do you envision eventually being able to cut that significantly, for example, through the use of your metrics?
Yeah, so the demo video I'm going to show you in a little bit here actually gives you visual attributes that say where the problems are. And so it's still the manual manipulation, unfortunately, but you can select groups of nodes to manipulate together. And we're currently exploring a snap to grid feature that allows you to allows the user to pull nodes to local minima for the readability metrics as they move them around, as well as feeding them back into automatic layout algorithms. Although these layout algorithms, though, tend to be very expensive when you start doing that, when you start optimizing for these things. All right, are we ready to move on?
Yeah, I think
Okay. Now, so let's talk a little bit more about these readability metrics. And again, I've been working on these with Ben Schneiderman back at University of Maryland. We have our network. We can code attributes of the network in colors and in shape and size and all these things. Here we just have colors. This is in the social action network analysis tool. And a refresh of our NetViz Nirvana, we want all these attributes to be satisfied by our final drawing. And we've created these readability metrics which measure how understandable these drawings are. Now, social action is a social network analysis tool created by Adam Perra at the University of Maryland with Ben Schneiderman, and incorporates statistical measures like NodeXL, like betweenist centrality and integrity and the like, with an attribute ranking system that allows you to see a tabular ranked view of these measures alongside the network visualization. And again, you have the net brushing and linking between them. And it has this multiple coordinated view approach. Now, this attribute ranking system allows us to very easily incorporate these readability metrics because we can just feed them in as additional attributes for the nodes, and we automatically get the coloring for them. We automatically get a rank table that shows you where the problems are in your graph. And we've added global readability metrics for the entire graph to social action, as well as our node and edge readability metrics that pinpoint the problems in the graph as they're moved. Okay. Now that popped up. Okay, so now I'm going to show you a brief demo of the tool in action here. Okay, so this is social action right here. You have continuous layout, where as the user modifies the layout, it continues to reposition the nodes around it. And we're loading in a small data set from the Alberta Politics Discussion News Group of people replying to each other. And then by tweaking some layout parameters, we can get to a good starting point to start our visualization. So what the user is doing here is they're changing the repulsion forces and the forces pulling nodes together so as to try to create a good initial layout. Okay? And once they've done that, they can rank by out degree or in degree or any of these statistical measures we have right here. They show up colored in the rank table on the side and then highlighted here in those colors. Okay? So the user can move to betweenness centrality or closeness centrality, and it'll compute these measurements for them, and they can do their entire analysis. Then when they're ready to publish the image, they freeze it, and then they start using the graph readability metrics. And so as they drag the nodes around, it updates the readability metrics for the entire drawing as well as for the individual node they have selected. And then they can rank by these metrics that are computed. So here we have no node occlusion, but we have a fair amount of local edge tunnels, which is where we have the edges traveling underneath nodes without connecting to them. And the worst nodes are highlighted in red, and the ones that are not so good are highlighted in kind of a dark blue. And then as the user moves them around, they get to this nice light blue color that indicates that everything's okay with that node. And so you can grab groups of nodes and move them together, control click, or you can create communities with your community finding algorithm and drag them together. But unfortunately, this currently involves a fair amount of manual manipulation to get to a good drawing. Okay? And then as you see, the colors are changed as the scale changes as well. So, all right, and that's the end of the demo there. But let's go through a static process of doing one of these analyses. So here we have this nice tight network colored by node occlusion. So the bright red nodes are the ones that are occluding the most other nodes. And up in the top right, we have a measurement for how many occluding nodes we have, how many edge tunnels, and how many edge crossings, just so you can get a visual idea of the count of these problems. The easiest way to reduce node occlusion, if you have the room, is just to spread the graph out. And unfortunately, in publications, you often don't if you still want to read the labels. But just by reducing the global spreading coefficient by an order of magnitude, we allow things to spread farther apart with our continuous algorithm. We substantially reduce the node occlusions from 4 down to 10, and then another order of magnitude, and we have a nice layout. Now, this might not be suitable for putting in a 2-column ACM format paper, because it takes up a lot more space, and when you compress it, you're not going to be able to read the labels. So oftentimes, in those cases, you end up with, again, doing the manual manipulation. Coloring by the local edge tunnels, we see those problem areas. We have 14 edge tunnels in total, and again, through manual manipulation, we don't have to move the nodes a whole lot unless there's a nice hairball in the center to completely eliminate the edge tunnels. In some tight graphs, it becomes impossible, and you just have to start reducing the amount of them rather than completely eliminating them. Edge crossings are a little bit more tricky because reducing edge crossings, oftentimes doing these gross manipulations like taking these highly central nodes and pulling them off to the side, or using good edge routing techniques. But currently social action only allows these straight edges we have right here. So we're limited to fitting nodes between these arcs of the edges from the high degree nodes. And so this improves our ability to do things like pathfinding, because we can easily follow the edges without the crossings, but it reduces our understanding of how important any particular node is in the network. So this guy looks a little bit less central because he's not in the center of the graph, and because his edges all come out from one side instead of from all around him. Right? And so if we just want to find paths, that's not a problem, but if we want to identify how important people are, being central and having your edges spreading around apart from you is a lot more important. And so this illustrates some of the trade-offs we often face when optimizing these metrics. We've looked at a bunch of additional readability metrics. Angular resolution is the spread of the edges around it. Also, the angle of the edge crossings can substantially impact pathfinding tasks and things like that, because users are more likely to follow the wrong path. We've looked at various things like node size and color and shape variance, especially when you have to scale your visualization, because beyond a certain point, you don't want to show the text on the node because nobody's going to be able to read it. You can just compress it. But you can't compress it too far, otherwise you're not going to be able to see the color or the shape of it. Additionally, we can look at the orthogonality, or how well the nodes and edges line up on an imaginary grid. And for UML diagrams or hierarchical structures, that's very useful because there's actually meaning to those levels. But for social networks and citation networks and things like that, forcing them onto these arbitrary grids implies relationships that don't exist. You can scan it more easily, but you have these relationships that don't exist there. Spatial layout is very important, and then there's also various measurements for the paths through the network, because you want these paths to be fairly continuous and easy to follow. So you don't want them to be very bendy, you want them to be nice and continuous, and you don't want arbitrary paths heading off towards nodes that they don't actually connect to, which is called geometric path tendency. And also, finally, you want edge lengths usually to be kind of uniform throughout your graph, except between disparate groupings. Oftentimes users then request that those be placed farther apart. So future work, like we've talked about, we have the snap to grid feature that we're working on, as well as feedback into these automatic layout algorithms. We've done this evaluation for NetViz Nirvana for teaching using NodeXL, this paper that we presented earlier. And then we've started implementing these readability metrics into NodeXL, so we can look at more long-term usage of them and see how well it improves users' end results. And so in conclusion, all the things that we've talked about here, the global readability metrics, as well as individual node and edge readability metrics for identifying problem areas. And we hope that this will help network analysts become more aware of these problems and how to fix them, and tool designers to give guidance to their users as to how to fix the problems in their graph drawing, so we can get better publications for everybody. Right, and if you're interested in reading the paper, we have a tech report here, and we're submitting that paper to CHI 2010. All right, thank you. Any questions?
So, yeah, you mentioned routing. How do you think that routed edges would affect, what do you think that there are readability metrics for routed edges that would still apply if you're going to change your strategy a lot?
So routed edges substantially would reduce the number of these blatant edge intersections and the edge tunnels underneath nodes. And so that is very helpful for pathfinding tasks and making sure that you actually find that the edge isn't connected to any particular node, that, because it's routed around the edge of it. But all of these metrics are applicable to straight edge drawings as well as routed edge or curved edge drawings. They just become a little bit more difficult to do. And with the routed edges, it seems that the path, the bendiness of the route and the angle of all of these junctions in the path, if you have line segments connecting it, starts becoming a lot more important. And if you have a lot of edges routed through the same narrow channel between nodes, that also becomes a bit of an issue, because then you have to do things like, instead of being able to code attributes of the edges using colors, you have to start using arbitrary colors to be able to distinguish the edges in those bundles. Right? And so currently our edge intersection metric would actually call those edges lying on top of each other as an intersection. So to properly handle those, we would have to extend it a little bit and make a measurement for how distinguishable any edge in that bundle actually is.
Do you have any thoughts on the graph with the edge labels? The examples you show, only the node has labels,
Yes.
right? But some graphs, edge also has labels.
Mm-hmm.
When you put the label on the node, it becomes a more complex problem.
So we just implemented edge labels in NodeXL, and our current approach is to line up the label along the edge and actually lay it on top of the edge with a light opacity bounding box around it. So you can actually see the edge behind the label, but it's not nearly as strong. And so this allows you to see intersections behind labels, even though hopefully you wouldn't have any of those. And it's gone.
Yes, but for edge readability, actually, the mapping between actual edge to the label of that edge is also important. It's not just about occlusion, right? There are many links, and you put some node. Sometimes users are not sure which link actually that label refers to.
So in NodeXL, because the text is actually tilted to the angle of the edge, and it's laid directly on top of it, it becomes a lot easier to associate those things. It becomes a little bit harder to read because it's tilted, but you have a lot less problems with it interacting with other edges and being able to identify which is which. What becomes more of an issue, though, is if you have long edges, do you stretch long labels out along all of them, or do you compress them? And if you have close edges where you don't have room for a label, what do you show there? And so we've looked at a bunch of various approaches for simplifying edge labels that we don't have enough room to show. and making them nice and unique so you can identify them and read them properly. And then we also have a label when possible approach where you rank edges according to your importance based on their betweenness centrality or something like that. And then it tries to label them just greedily along that list. And then if it can't show a label for that edge without completely destroying the readability of that section, it just won't. And it will tell you that it can't show an edge there with maybe a little marker or something like that.
Any other questions? Okay, then let's thank the speaker one more time.
Thank you.
Okay. Thank you.